So, welcome student to the next class of Introduction to Nonlinear Optics and its application. Today we have lecture number 47, and in the previous lecture we try to understand under pump depletion condition how third harmonic wave should evolve. In order to calculate that thing, we assume that there should be some quantity that is a constant of motion, and we find that if this constant of motion is there, then from that we can extract few information, and we find a differential equation of u1 and u3, where u1 and u3 was the amplitude of the corresponding fundamental and third harmonic wave. So, equation is little bit modified. So, we will start from that point. So, in today's lecture, so we will the third harmonic generation under pump depletion condition, this calculation I will like to finish today. So, the continuation of that thing, and then we study something called cross phase modulation, which is very interesting. Well, so this is the expression that we had in our last class. So, constant of motion, as I mentioned, there is one quantity that seems to be not changing with respect to z, and that is this. So, amplitude equation is a equation that gives you how the amplitude u1 and u3, amplitude of the fundamental and amplitude of the third harmonic will going to evolve. They are coupled to each other. So, that is why you can see in the right hand side there a coupled equation, and this constant of motion give us an additional information regarding the relationship regarding the value of psi, which is the relationship between the phases of these two waves. Remember, psi is equal to phi 3 minus 3 phi 1. So, there is a phase relationship. Psi basically gives us a phase relationship. So, this phase relationship suggests that the value of this quantity is pi by 2. Once we know the value of this is pi by 2, we have a modified expression in our hand as far as the amplitude of the fundamental wave and third harmonic wave are concerned. Once we have this equation, next thing is to solve this. That is the main issue here, how to solve this coupled equation. So, in order to solve this, we need to find few more things that what this equation suggests. These two equation, whatever we have here, can gives a very important information, and that information is the intensity or the total energy of the system remain conserved. So, if there is no loss, these two equation does not contain any kind of loss. Only thing these two equations suggest that some of the energy can come from u1 to u3. That means third harmonic will generate, and third harmonic will generate as a result of the generation the decrement of the fundamental wave. So, fundamental wave basically gives some kind of energy to third harmonic wave, so that the third harmonic wave will going to evolve. So, there is some sort of energy exchange between these two quantities u1 and u3. So, they are coupled with each other, that is why. So, even though the energy is changing from one to another, the total energy or the total intensity, if I write in terms of intensity, should remain conserved. So, there should not be any kind of loss of intensity or any kind of gain of intensity with this process. If I say this is the total intensity. So, total intensity is I1 plus I3, intensity of the fundamental wave plus intensity of the third harmonic wave. So, I can write it is half epsilon 0 C n1 u1 square, because this expression every day, almost every day we are using this expression. So, by that time I believe you are now in a position to appreciate this expression. If it is 1, it is square. So, mod of u1 square is nothing but u1 square, mod of u1 square is nothing but u1 square. In the similar way, mod of E3 square should be equal to u3 square. So, these two equations we have, and once we have these things, then the next things to find out whether the I will going to change or not with respect to z, we make a derivative over that. So, once we make a derivative, so I have the derivative with respect to u and the derivative with respect to u3 and u1 like this. And now, the derivative with respect to z du1 dz, I can put the value from here. In the similar way, del u3 del z, I can put the value from here. Once I put this value this from here and put this here, then we will readily see that this quantity will be 0. That means I, the total intensity, remain conserved. If the total intensity remain conserved, then again we can write that half of epsilon 0 C n1 u1 square at any z point plus half of epsilon 0 C n3 u3 square at any z point should be equal to whatever the intensity we have in the input. So, this quantity is the intensity at input, and you can see that this quantity only have u1 square, and the 0 suggests that it is at z equal to 0. Why only one term is here? Because there was no third harmonic wave at z equal to 0 point. So, that is why we have only one term. So, from this equation I can have a relationship between u1, u3 and u1 0, which is the amplitude of the fundamental wave at z equal to 0 point, which is non-zero. So, n1 u1 square plus n3 u3 square is equal to n1 u1 0 square, where n1 u1 0 is the amplitude at z equal to 0 point. So, this is an additional equation or additional relation we have, which help us to calculate or the solve this differential equation. So, let us this coupled differential equation rather. So, let us try to find out how to solve this coupled differential equation and what kind of expression we have under pump depletion condition, the evolution of the third harmonic rather. So, we have this expression, this is the expression that we have just derived. Now, from here we can write u1 in terms of u0 and u3. So, u1 square is u1 0 square. I just divide everything with n1 and put this u3 to that side. So, I will have this, and the ratio of n3 and n1 I write this constant quantity as b. So, my u1 square is now equal to u1 0 square minus b u3 square. Now, go back to our equation for this third harmonic wave. So, if I go, so this is the equation I am looking for. So, I need to solve for this equation. So, here u3 is here, but in the right hand side we have u1. So, if I somehow able to change this u1 in terms of u2 in terms of u3, then we can solve this. So, that means we are trying to decoupling it, and this decouple process I can use this relation that we essentially we are doing. So, del u3 del z is equal to kappa 3 u1 cube, and just above we just write u1 in terms of u3. So, if I now replace this u1 with this u3, we will have u1 0, which is a constant term, minus b u3 square whole to the power 3 by 2. Now, you can see that this equation u3 in the left hand side and right hand side also we have u3. So, that means we can do this integration, and if we write this integral forms, and then it will be d u3 divided by this quantity. In the right hand side it will be kappa 3 integration of dz. Now, the next challenge is to just find out the solution or the integration of this quantity. How to integrate this, that is only challenge, because in the right hand side this quantity is nothing but kappa 3 multiplied by z. If I integrate to from 0 to z, both the cases I am integrating it from 0 to z. So, this will be the limit, but before that we need to know how to basically solve this integration. how to integrate these things. So, we have in the right hand side the solution is basically here. So, d u3 divided by u1 0 whole square minus b u3 z square whole to the power 3 by 2, I can write in the two part. One is this and another is this 3 by 2 I can write is 1 plus half in this form. This is the standard way to write this form. Once we write these things, then I took u1 0 minus b u3 square, this quantity, that means entire this quantity, as x square u3 z square of that. I just replace these things to another variable x and write in this way. Now, if I make a derivative of both the side, in the left hand side I can write minus b u3 del u3 is equal to, in the right hand side, because both are the variables now. So, 2 x u3 square dx plus 2 x square u3 du3. From here we can find an interesting expression that d of u3 is x u3 divided by b plus x square dx. So, my entire equation is now transferred to dx. So, d u3, this quantity is simply x u3 divided by b plus x square, and in the denominator also we have this quantity u3 minus b u3 z square whole to the power half. This quantity is nothing but cube of this quantity, because if I write to the power half and then it should be this entire things is 3 by 2. So, this 3 by 2 basically come here. So, du I replace, when I replace here du, so du will be replaced by this part, and the rest part is basically whatever the thing we have in the denominator, and in denominator we have x square u3 x cube u3 cube. Now, if I look carefully these things, so b plus x square, then u3 square is equal to u1 0 square. From here I can write these things straight away. If I write this b this side, then b plus x square, if I take common u3 square, then b plus x square u3 square is nothing but u1 square. In the numerator you can see that we have b plus x square multiplied by u3 cube. So, if I write b plus x square u3 square to u1 0, so this is constant term, and another u3 is sitting here, but in the numerator we have another u3, so that will cancel out. So, if this is cancelling out, so we will have 2 here, and this I can replace, and it will be simply u1 square. So, the total expression, the total integration become quite simple, and here in this slide we can see that integration of d u3 divided by u1 0 square minus b u3 z whole to the power u3 z square whole to the power 3 by 2 with the proper transformation, I can write this in this simple form. So, now d u3 can be replaced by dx, where the transformation was, if you remember, that u1 0 square minus b u3 square is equal to x square u3 square. That was the transformation I used. So, now we are in a position to solve this straight away. So, if I now integrate these things, it will be simply this negative sign will absorb, and we will have simply 1 divided by u1 0 square x, that should be equal to kappa 3 integration of dz that we have from the beginning. Now, we replace this x in terms of u3. So, if I replace this x3 in terms of u3, in the right hand side it is simply k3 kappa 3 z u1 0 whole square with the limit 0 to u3 in the left hand side. And if you do a simple calculation and take u3 one side, then you will have an expression u3 like this. So, this is your solution. This is the solution of u3, and this solution you can do by just simply doing this integration, and this basically give us how the u3 or the third harmonic will going to evolve. Once you know what is your u3, then readily you can calculate what is your u1, because we have an equation in our hand. We have a relationship between u1, u3, and this is the equation I am talking about. So, this equation you will have. Now, you know what is your u3. So, you just put your value of u3 and you can readily find out what is your u1. So, once you do that, so I want the student to do that calculation by your own hand and check whatever is written here is the correct thing or not. Once you do that, you will have an equation like this, So, now if I put the boundary condition and check what is happening, as soon as I get the expression of z, then the next thing is to find out what is the boundary condition. And if you look very carefully about this u3 equation, the boundary condition suggests that at z equal to 0 point, u3 should vanish. It is really the case? Yes, it is really the case. u3, if I put z equal to 0, this quantity will not be will vanish. So, it will be 0, and in the numerator we have z equal to 0. So, this quantity will 0, entire quantity will 0. Again, another boundary condition is at z equal to 0, u1z should be u1 0. So, u1z solution is also in our hand. So, if I now put z equal to 0, you can see that this quantity will not be there. So, only u1 0 will surviving. So, we will have both the boundary conditions satisfied with whatever the expression we have in our hand. So, these two are the expression of the evolution of u1 and u3 under pump depletion condition for third harmonic generation. So, now the next thing is to plot these two equations as a function of z. If I plot these two equations as a function of z, you can see that this kind of figures are here. This is a quite physically justified figure, because this green line suggests how u1 is going to evolve. This is for u1, evolution of u1 as a function of z, it will going to evolve like this. Rather, I am plotting u1 square, and the blue line for u3 square z. So, u3 is going to evolve in this fashion. So, quite this is a quite expected thing, that when I launch the fundamental field here at z equal to 0 point, the total energy was here, which is the fundamental wave, and gradually what happened is fundamental wave is decaying, the energy or intensity is decaying, and as a result what happened, this energy will use to feed the third harmonic wave. So, third harmonic wave will going to evolve, but it will not going to evolve to an infinite way. So, it will evolve and go to a saturation point, which is quite justified, because we know that when it is vanishing, so there is entire power is now converting from this to this. So, it will not going to increase more like we have in the previous treatment. It is increasing is a parabolic way, it will not be like a parabolic way, it will go and then saturate. So, once we calculate the pump depletion condition, then only we can have these things in our hand. Well, now the next thing I like to discuss is the cross phase modulation. So far we are dealing with third harmonic generation, and the discussion of the third harmonic generation is almost finished. So, we now go to another important phenomena which is called the cross phase modulation. Well, the cross phase modulation is nothing but the extended version of cell phase modulation. In the cell phase modulation, what happened if I launch an electric field, this electric field will modify the refractive index by its own. That means, if I launch an electric field, if you remember the expression, refractive index, this is a Carr effect, was n 0 plus n 2 I. So, I is the intensity of the launched light. When the light is launched, the intensity of the light basically leads to the change of refractive index, and this change of refractive index is coming through this Carr coefficient n2. If n2 is non-vanishing, it has a significant value, then we have a significant change of refractive index, and this is happening because the pulse itself is modifying its refractive index. But what happened if in that particular system we launch not one wave, but two waves as shown here, E1 and E2 with frequency omega and omega 2. So, what happened for these two waves, that the refractive index is also modified, and this modification will be twofold. One modification will be due to its own way with this, and on top of that what happened, because of the presence of other wave, also the fundamental wave, if I say this is a fundamental wave, this fundamental wave will experience a change of refractive index due to the presence of other wave. And here the change of refractive index is shown is 2 n2 ni. So, you can see that n2 ni is a change of refractive index, but the refractive index will change for fundamental wave. That means, fundamental wave n1 suffix suggests that it is for E1 wave. So, E1 wave will going to see the refractive index, and this change will be done by other wave, and it is vice versa. Also for other wave, E2 wave, the refractive index n2 will going to change, and the reason is the other wave or the fundamental wave I1. So, this is that is why it is called cross phase modulation. The phase modulation is still there, but it is crossing over. So, one is, so we are basically manipulating light by another light. So, by definition, if I write, the cross phase modulation is the change of optical phase of a light beam caused by the interaction with another beam in a nonlinear medium or specially a Carr medium, because in Carr medium we have n2 not equal to 0. So, that is why for Carr medium it is more evident. Now, the calculation wise it is straightforward. So, E1 and E2 are the two waves that we have. So, I can write these two as a plane wave. Then total electric field is E1 omega plus E2 omega. So, nonlinear polarization, when I calculate, it should be ET cube. So, ET is the total. So, that means I am making a sorry, here should be a cube, it is not square, it is the mistake. So, once we make a cube of these things, so there will be many terms. So, the terms that will contain 3 E1 square E1. So, we know that this degeneracy concept, that if these two fields are different, then we have a quantity 6 degeneracy factor. If any one is same, then it is 3. So, you can see it is E1, E1 star and E1. These three combination can give rise to this mod of E1 square E1. So, this E1 and E1 are same. So, that is why we have a degeneracy factor 3 here. For this case, we have E2, E2 star and E1, 3 distinct fields are there, that is why the degeneracy factor 6 is sitting here. So, we can calculate the cell phase modulation and cross phase modulation term with P nonlinear, and once we have this P nonlinear term in our hand, then we can readily solve the nonlinear Maxwell's equation. This equation we have solved several times. Only thing is that in the source, instead of having P cell phase modulation, we have cell phase modulation plus cross phase modulation term both together. So, now these two things I will put my nonlinear Maxwell's equation. This is a old process that we have been doing. So, if I want to find out the evolution of only U1 wave, so it will be E1, E1, and this is our source term which contain both cross phase and cell phase modulation. This treatment is almost similar the way we calculate the cell phase equation for cell phase modulation, only another additional term is there. So, we calculate this quantity and then we calculate the next one, and eventually we have an expression like this. Interesting thing is that instead of having one term here, we now have two term, and this second term is basically the contribution of cross phase modulation. The treatment is, as I mentioned, straightforward. For cell phase modulation, we are doing the similar kind of treatment. Here we are doing the same thing, and basically this leads to a straightforward expression, and this straightforward expression is, so let me go back to here. We have 2 of I of k1 d E1 dz and minus of 3 by 4 and their quantity. So, if I write this 2 and k1 downstairs and mu 0 epsilon 0 like 1 by c 0 1 by c square, and if I manipulate few things, then we can readily find this expression. So, this is not a very new thing. So, this kind of things we have done. So, here this is the thing, you can see that 1 by k1 term is there, 3 by 8. So, minus I can be absorbed, minus 1 can be absorbed this I term. Important thing is what we are having here, we are having mod of E1 square plus 2 of E2 mod 2 E2 mod of E2 square E1. So, finally, we will have this expression, and in this expression again this is the term which is basically the cell phase modulation term, and if I write this coefficient as gamma, then we have a relatively straightforward expression in our hand, and this is the expression for cell phase modulation and cross phase modulation both. This is basically the term related to cross phase modulation XPM, and this is for cell phase modulation SPM. One is XPM and another is SPM, and since this term is crossed, E1 and E2 they are crossed, that is why it is cross phase modulation. E1 and E1 is same, this is for cell phase modulation. Exactly in the similar way, exactly in the same way, one can calculate the cell phase modulation for E2 also. So, this is for E1, so another wave is still there E2, and if I write this E2 expression, so everything will same, only this coefficient will slightly change, because in coefficient we have omega 1 and n1, now it should be omega 2 and n2 as is written here, and E1 square is replaced by E2 square and E2 is replaced by E1. So, here this is my cross phase modulation term and this is my cell phase modulation term SPM. So, cross phase and cell phase modulation term is still coming here, and this is the E2 field, and we have a set of equation which basically gives us the idea of cell phase modulation. So, with that note, I would like to conclude my class here. So, today we will learn very important thing, how under pump depletion condition the third harmonic will generate and how this will going to evolve. That is the first thing, that the first part we have done. In the second part we understand what is the cross phase modulation. So, cross phase modulation is nothing but if I launch two different wavelength, two different light strong beam. So, one beam will be modified, the refractive index of one beam will be modified by another beam, and because of that we are getting two differential equation which seems to be a coupled differential equation, and these two equation basically govern how the phase will going to modify. But in the next class we try to find out because of this cross phase modulation, is there any change in amplitude or not, or the amplitude or the total energy will remain conserved or not, and then we try to find out how the phase will going to modify. As the name suggests, is a cross phase modulation, so obviously the phase will going to modify. So, these kind of things we will check or do in the next class. So, with that note, let me conclude here. Thank you for your attention and see you in the next class.